Welcome back to the podcast, everyone. Today I'd like to welcome Professor Christine Doan. She's a professor at Durham University, and I was hoping today that she would be able to tell us a bit about her research.
Okay, thank you. So I work on black holes, and which is fabulous. What's not to love? We've all watched the science fiction movies where they get linked to time travel, travel through space with wormholes, alternate universes, all the really cool stuff. Well, I don't really do that. What I do is look at material falling into black holes. When material falls under such strong gravity, you get enormous amounts of energy out. And this matter glows not just red hot or even white hot, but it glows X-ray hot. And so you can look at these accretion disks around black holes if you look in X-rays. But X-rays don't get through our atmosphere, so to do that you have to go above the atmosphere, which means you get to play with rockets. I'm a rocket scientist. And that's a great way to describe yourself at parties.
Okay, so I read a bit about your PhD. Was that like directly related to the research you're doing now, or?
Yes, in many ways, that's a common thread in my research. Is I've ever since my PhD, I've been looking at material falling onto black holes, looking at how that enormous gravitational potential energy gets converted to the X-ray radiation that we see.
Okay, so how would you say what you're doing now is sort of building from what you've done previously?
So when I started in research, doing my PhD, I was looking at that X-ray radiation, and it's incredibly intense. You get really very high luminosities in X-rays if you have lots of material falling towards the event horizon of a black hole. And then you can get photon-photon collisions, and you can produce an electron-positron pair. It's Einstein's most famous equation, E equals mc squared. Energy and matter are kind of equivalent. And so if you have photons of high enough energy and you smack them together, you can make matter-antimatter, you can make an electron-positron pair. And so my PhD thesis was looking at how that process changed the X-ray emission that we actually saw, with high energy, the highest energy X-rays being absorbed in these photon-photon collisions and making us more electron-positron pairs.
Okay, so I guess that's kind of was that how you started in this kind of black hole X-ray kind of field? Very
much so. So it started off very theoretical. I built a code that could stop most computers at the time, which was always a lot of fun. I stopped NASA's Cray at one point. That really felt like an achievement. But I also got more and more interested in how we could use observational data to test these models. And so I started talking to the people who understood X-ray data, and that was very exciting. And in many ways, that's what I do in my research now. I take the best available theoretical models, and I take the best available observational data, and I make them talk to each other. I make them go into the same paper, and normally they miss by miles, but that's okay, because that just shows us the things that are missing from our current best understanding.
That's interesting. So you're like linking together theoretical and experimental physics.
Yeah, very much so.
Would you say you have like a preference for theoretical or experimental kind of sides of things?
Yes, I'm very clearly a big picture person. I want to understand the big picture. What is the structure of this accretion flow? What are the main physical processes that we need to understand? What's the physics that's going on? Often there's a huge load of work that goes on behind that, making computational models, making theoretical models. But I want to get a big picture of what happens as the material falls in towards the black hole.
So is that more towards the theoretical side then?
Yes,
What is it but?
But you can make any theoretical model you want. I want it to be a good representation of reality. I want it to actually match up with what we see.
I guess that's the ideal, right?
Yes.
Okay. I guess I'm quite curious, how did you choose like black holes and that sort of thing for your PhD topic?
What's not to love? Who wouldn't choose black holes? I think I'd been fascinated by some of the storylines in the science fiction. I grew up where Star Trek was the most exciting thing on TV, and just the ideas that they play with in terms of time travel, space travel, and I especially liked the character of Spock, the science officer, who's the half human, half Vulcan, and he's the one who understands what's going on. Generally, actually, it's him who rescues everybody from whatever trouble they're in, because he thinks it through and starts to understand what's going on and can think of a way out of it. So yeah, I wanted to be Spock.
That's not a common answer.
Yeah. Sadly unachievable. I never grew the ears.
You can always hope. Okay. Well, you mentioned earlier that you work at NASA, and I think I've read that you work as part of like an NRC fellowship.
Yes.
Could you talk about a bit on like what that actually is and how you got the position?
So academia is a somewhat tricky career path to follow. In general, after your PhD, there's some time spent on short-term contracts, and that's an opportunity, but it can also be tricky, because often you don't know what country you're going to be in 2 years' time, or even what continent you're going to be on in 2 years' time, which, yeah, is both exciting and sometimes difficult. But after my PhD, I'd applied for fellowships, because they give fellowships, the money goes to you, and so you get to choose the projects you work on, whereas if you work with a group, they get to choose the projects you work on.
Okay.
So I'd applied for fellowships, and I'd also applied for various jobs with groups, but this particular fellowship came off, and so I worked for 2 years in the United States, in Goddard Space Flight Center, which is just outside Washington, DC. And that was just a really exciting time to go and live and work in another country. It's very different from visiting another country. You've got to figure out how to get an apartment, how to do all the kind of normal things of life, but in a different country where you don't know what are the chemist shops called, and you just don't know anything.
Yeah, like moving into Durham, like getting into the routines and things is very weird. Like you don't do that when you're just visiting somewhere.
That's right. You have to actually set up a life,
yeah.
And in another country that comes with lots more kind of surprises.
Okay, I'm quite curious. Would you say like the way science was handled was different in any way in America compared to the UK? Like, any cultural differences or anything like that?
There were some cultural differences, because I was working for NASA. So I was working in a science group, and so that had a very similar feel to the group I worked in for my PhD. But because it was also part of a much wider institution, and that institution involved engineering and flying satellites and buildings where you weren't really meant to go, especially as a foreigner, and so it was a very different sort of dynamic, because it was part of a big institution of NASA, as well as being a science group.
I see. Okay. Could you talk a bit about like what things you did in your placement at NASA?
So that was very much a kind of continuation of the work I'd done with my PhD. Again, I was looking at the structure of material falling into a black hole, But the group that I was part of, they were also involved in flying an X-ray telescope in the payload bay of the space shuttle. And they needed extra hands. so an unexpected part of being kind of a theoretician was I ended up in the control room of the space shuttle, Goddard Space Flight Center, wearing the snazzy headset and controlling the telescope in the payload bay of the space shuttle.
So were you actually directly using the controls?
No, I was the planner, so I'd be planning the timeline, what they would look at when you'd have to schedule in the slew times and the sun avoidance and all sorts of fun stuff.
It's very cool. The closest thing I've got to anything like that is like crashing a remote control helicopter.
Yes. So sadly, I didn't get to play with the controls. However, having said that, the shuttle astronauts did.
Ooh.
So on the way towards the end of the mission, we were stowing all the telescopes, and there was a bit of a problem with the pointing on our X-ray telescope, but everything else had stowed. So the shuttle crew said, "Okay, we've still got some time. Do you want us to point?" And we said, "Yeah." So we got them to. We got a nice big target, a supernova remnant, where there's X-ray hot glowing gas over quite a large angle for. And they piloted the shuttle with trying to keep it always in the field of view. And we did a random walk over the supernova remnant and got good data until the very last moment where we had to close everything down. And they really enjoyed that. It's like, hey, we can show we're hotshot pilots. And we got extra hours worth of data.
That does sound quite exciting. Okay, so after your placement at NASA, that's when you came to Durham, is that correct?
No, I went via another 2 years, so I had another fellowship, this time from the UK, and I worked at Leicester in their space science group. And again, they have a group that does both models and a lot of observational data. They've built several X-ray detectors for satellites. And so I was working with that group and using X-ray data from some of the instruments that they had developed.
Okay, was that building on through your previous work, or were you doing kind of new
Yes,
things?
in many ways. So I think as part of my thesis, one of the projects I did was looking at X-ray emission from a supermassive black hole. So we had X-ray data from one of these space satellites, but we also had optical data simultaneously with that satellite from one of the telescopes on the Canary Islands in La Palma. It's such hardship being an astronomer. You have to go to all these. And so I was at the telescope in La Palma, and I did get to drive that one.
Ooh.
That was a lot of fun. And we got simultaneous data, which was some of the first X-ray optical simultaneous data from an AGM that anyone had ever got. And that was an instrument that had been built by the Leicester Group in collaboration with the Japanese. And so I started this collaboration with the Japanese Space Agency, and when I was working for NASA, I got to go to Japan. It's such a hard life. I had to go to Japan.
Oh, if you have to, yeah.
And started working with the group in Japan. And continued that collaboration as well. So in fact, 5 years ago, I had a sabbatical year and went to live for a year in Tokyo. Such hardship, you have no idea.
Okay, so I wanted to actually talk about your year in Tokyo a bit later on, but for now I wanted to mention if you had any particular reason for coming to Durham? Or...
yes, in many ways. So I got another fellowship, which was then a longer term fellowship, a 5-year fellowship. And the plan had been that I would stay in Leicester in their space science group, but my husband's also an academic, and he'd just got a position in Durham. And because fellowship goes to the person rather than to the group, I could move my fellowship and come up to Durham and be part of the group here.
Okay, I see. It must be quite hard, like managing like a personal life, trying like when it seems like you have to be moving.
Yeah,
and things like that.
Two career couples. It was very difficult. We were 9.5 years on short-term contracts, and at various points we got out of sync, and so it was every year one or other of us was doing the job round, and is it this time that one of us has to give up the academic career that we both really wanted? But it turned out okay in the end. Grace of God. I mean, but it was very difficult.
I see. So, about your year in Tokyo, I was hoping you could expand on that.
Oh, that was amazing. So I've continued working with every major space agency on the planet, apart from the Russians, and that's looking more and more like a really smart move. But doing this combination of the best possible models and the best possible data. And so it became, I had this long-standing collaboration with the Japanese. They have this really innovative space program where they fly really novel instruments, but in quite small payloads, and every sort of 5, 6, 7 years there'll be a new Japanese X-ray satellite doing with new discovery space, and so I'd been involved in one of the previous Japanese missions and had gone for 3 months to Japan and worked on that data, and so it was just a great opportunity to be part of a live mission, especially close to the launch when the new data are coming down and they show us new aspects of what the accretion flow is doing. And so because of this long-standing collaboration, I was on the science team for this new mission, which was called Hitomi, and it had the best spectral resolution ever. It had such discovery space. Spatial resolution shows you beautiful images, but spectral resolution gets you dynamics because you can see from the Doppler shifts how the material's moving. So it had this spectral resolution. It was going to show us the dynamics of the material around black holes. And the day we left to emigrate to Japan for a year, there was a problem with the satellite, and it basically fell out of the sky. It was, I'm sitting on the plane, emigrating, thinking, la did my satellite just fall out the sky? And, basically, yes. But because I'm half a theoretician, actually, with their incredible new data, anyone could have written fabulous papers with the new data that satellite would have given us. But I'm also a theoretician, so I had ideas for projects that we could do on existing data that meant that my time there was very fruitful, actually, because I had lots of graduate students whose thesis was basically, and there will be awesome new data from this awesome new satellite, and now they're going, I wonder if Chris has got any ideas. What can you work on? I was like, oh, okay.
Oh, that must have been quite intense.
But yeah, just living in Japan for a year and just setting up a flat in Japan. We set up a flat in Japan and we really lived there. We weren't in the kind of university housing. We were in a standard town close to the train station, so we could, my husband was also working at a university there, and so we could both commute to our respective places, and we lived in Japan and more than survived, even though my Japanese is rubbish.
No, my mind's gone blank. It's okay, I can edit a pause out. Yeah, so I know I sort of asked you this before, but I'm really curious if there were any sort of cultural differences while you were in Japan.
Oh, many.
What, both in terms of the science and then also just day-to-day kind of things.
Very many, but it's actually a culture I feel very comfortable with, even though I can't speak Japanese. So some of the ways you do science are a little bit different in that it's much more about building consensus. Having worked in the States and worked in Japan, they are opposite ends of the spectrum.
Oh, yeah.
So in the States it's very individualistic, whereas in Japan it's very much more communal. And actually, being in those two very different cultures made me realise, actually, I'm really European. Because at some point you have to balance individual and society. And in the States it's very much individual, and in Japan it's very much society. And I think Europe actually has a really good balance of individual and society, because both are important. But I would think that because I'm European. But it did actually take living in such very different cultures to make it very clear to me that, okay, in Europe we have many different languages in a very kind of small size scale, but I have more in common culturally with someone who speaks a very different language than me than I have with, say, in the States, where they speak the same language, but the culture is actually surprisingly different.
Yeah, it's kind of like, you can try a bunch of different new foods when you go to uni, but nothing beats mum's home cooking.
the food in Japan. The food in Japan. The food in Japan probably beats. It's really fantastic. I'm just walking around Tokyo. It's a really dynamic city. There's places where there's just kind of blazing lights and sound and huge mega screens and people everywhere. I grew up in a fairly scruffy seaside town that's kind of back end of beyond, and I get to go walk around Tokyo, this glitzy mega city, and that was just amazing.
Yeah, I really like to be able to live in a kind of big city like that, at least for a while. I think it'd be really eye-opening experience, I guess. Yeah, definitely different from Durham.
Yes. Well, I did my first degree in St Andrews, so there is smaller than Durham, there is further north, and there is colder.
The big three.
Yes. Yes, often my first few cheese come November and December we'll be going, ooh, is it always this cold here? And I'm going, wait till you find February.
Okay, so I guess now could you talk about what you're doing currently, research-wise? Are you still going in on the accretion disk?
I'm still trying to understand how the material falling towards the black hole, what's the nature and geometry of that accretion flow? What are the physical processes that are important? How does that determine the wider emission that we see from these objects, like in supermassive black holes? we find these supermassive black holes and quasars from this the activity generated by the accretion flow. There's very strong ultraviolet and X-ray radiation, that's ionizing radiation, and so it makes a lot of emission lines, and we have this characteristic feature of quasars called the broad line region that we see both in local active galaxies and in quasars out to the edge of the observable universe at redshift 7, and they look just the same. There's clearly some physics going on here about how you form this broad line region, where the material comes from. It has a structure, and we don't really understand that structure because we don't really understand the physics of how these lines are formed. It's obviously not just kind of random bits of material falling in, because then it wouldn't look the same from now to the edge of the observable universe. It's clearly got a well-defined geometrical structure, a well-defined dynamical structure. It's connected somehow to the accretion flow. My best guess is it's some form of wind coming off this bright accretion flow. We could do with knowing what form of wind and what the dynamics actually are, and then we'd actually understand what it is that we're using to identify quasars from here to the edge of the universe.
Okay. Do you have any ideas on what you're gonna data's gonna show in the upcoming future? Or
well, next year they're going to relaunch that satellite.
Ooh, exciting!
I know.
Would you be going back to Japan?
So I'm going back to Japan.
Ooh, okay.
So I'm going back I'll go back in October this year for a short visit of a few months, and then I'll go back October next year. You might have noticed I'm not going in the term that I'm teaching, so I don't have to lose all my nice teaching. Because I found the last time I went for an entire year that obviously I had to give up my teaching, and then you can't just get it back off the person who put all that work into doing the course. So yes, I'm not going to do that to my teaching. I'm going to go in shorter chunks of time. But still, I'm very much looking forward to travelling again.
Yeah, it does sound quite fun. Yeah. So would you say about teaching something quite important to you then?
I really enjoy seeing the light go on behind the eyes. I like being able to explain the physics. Often things can get very technical, and the technical bits are really important, but I want people to understand the big picture as well. I want people to understand it's not just maths that they're doing, it's something connected to the real world that we can start to understand.
Okay. Do you have anything you want to mention?
The highlight was a couple of years ago, the BBC came and said, do you want to be part of this new series we're doing on the universe? And I'm going, yes. So they took me away in the middle of lockdown, and we did some filming in a Welsh quarry, and it was such fun. It was really very interesting trying to work with a full film crew and trying to explain the concepts that they wanted in the right level and in an engaging way. That was a lot of fun, so I really enjoyed that. But actually, when we lived in Japan, I had another inroads with the BBC. Actually, this was Radio 4. Radio 4 contacted me because I also do talks on science and faith. I'm a Christian. And they said, would you do a Lent talk for us? And I said, yes, I'd happily do that, but I live in Japan, so sorry. And they go, no, it's fine. We'll find you a recording studio in Japan. And so they give me this recording studio in Japan in the really snazzy nightlife district. And I have a live link to my producer in Manchester. I was just like, this is amazing. We've got to remember, I'm a girl from this scruffy little seaside town. My family aren't anything special. Me and my sister, we were the first generation in our family to go to university, so we're first generation scholars. And I get to sit in a recording studio in Roppongi in Tokyo, in the glitzy nightlife area, with my live link to a producer. It was just epic.
A bit more high end than the phone setup we got right now.
Whatever works.
So it was that kind of like Brian Cox style kind of documentary?
Very much. So it is the Brian Cox one, which they do for the UK market. But the rest of the world apparently isn't that keen on Brian Cox.
Oh, boo.
We prefer a variety of talking heads. Well, not exactly talking heads. We spent a lot of time walking around quarries. It's surprisingly cold on a Welsh quarry.
Comparable to St Andrews?
Well, at 11 o'clock at night, where we're in an abandoned building, an abandoned industrial building, it got very cold. Even though I was wearing I'm wearing the proper stuff. But yes, that was cold, but a lot of fun.
Yeah, scientific communication like that does sound quite fun actually. Like, I've been thinking of doing scientific research for a while, but now, like, I guess we're starting this podcast and some other things. Like, that does sound like it would be quite a fun thing to do as well. Like, maybe even if like it's just bits and pieces here and there, and still like a whole career.
Yeah. Now I enjoy doing public talks. So I was in a school a couple of months ago. Part of it was International Women's Day as well, and just giving them a talk about doing science and why it's not this kind of lone genius of questionable social habits, which I think is how most people think about scientists. But if you're going to do rocket science, you need a very big team. You need a team of people, you need a team of engineers, you need a team of chemists, you need a team of computer scientists, you need the scientists who are going to interpret the results. You don't just need some lone genius, you need a team to do big projects like this. And so just trying to give them this idea that science isn't about being some genius, that you just happen to be able to do science, that just does not happen. I saw the first maybe 5 minutes of Good Will Hunting, which is this film with Matt Damon, who I normally really like. But the whole premise of the film is there's a janitor who just happens to be a mathematical genius. You don't just happen to be a mathematical genius. There are people for whom that way of thinking comes more easily, but it's a language. And even for people who are really good at languages, you have to take the time to learn the vocabulary. You can't just, even if you're amazing at languages, you can't just speak Japanese, and you certainly can't read it. It's just ridiculous. And yet people get away with writing film scripts that basically say you can just happen to be good at tensor mathematics. I'm sorry, you can't. You happen to have to practice and work really hard at it. And then some people will always find it a little bit easier to think that way than others, but no one can do it without practicing a lot.
Yeah, but it's like Einstein has his so-called miracle year of 1905,
yes.
Whatever, where he bashes out 5 bangers of a paper. But calling it one miracle year makes it seem it's just genius. But you must have taken so much many years of hard thought and effort to actually get to that point.
Yeah.
I'm sure it doesn't just happen.
Yes. Yes. And so for my first years as well, it doesn't just happen, you have to work at it.
When I'm doing the quantum mechanics weekly problems, I gotta say I do wish it would just go. But maybe we'll get there eventually.
Yep. I think I've made you all at least have a go at thinking what a particle in a box might do. I think I got you to think intuitively and physically about that. But we will see. I've set you a tutorial. You will find out.
Ooh, okay. I'll mark that in my calendar. Okay. It's been so nice talking to you, Chris. I think we'll wrap it up there.
Okay, thank you.
Thank you very much. I think that was